You know that feeling when you're trying to hear someone whisper across a packed, super noisy room? It's pretty much impossible, right? The voice just gets swallowed up by all the chatter. Well, in the world of radio, there's this system, it's called WSPR, that does something even crazier. It pulls perfectly clear messages out of what sounds like a hurricane of pure static. So how on earth does it do that? Let's get into it.
See, every single radio signal, it doesn't matter how strong it is in for a fight. It starts out as this beautiful, clean signal, but then it has to travel through our atmosphere, which is just full of noise. And I'm talking about everything from lightning strikes halfway around the world to solar flares, not to mention all the other radio signals bouncing around. By the time it gets to the receiver, it's often this distorted, unrecognizable mess. And that really brings us to the big question, doesn't it? How in the world do you find one tiny, whispered message that is buried under a literal mountain of random, chaotic noise? I mean, it sounds completely impossible. But it turns out, WSPR has a ridiculously clever solution.
To really appreciate just how genius this solution is, we first have to get our heads around the scale of the challenge. We're not talking about just a little bit of static here. We're talking about a signal that is, for all intents and purposes, completely invisible to us.
This number right here, minus 28 decibels, this is where things get wild. This is the signal-to-noise ratio, the SNR, that WSPR can pull a signal out of. To put that in perspective, it means the noise is more than 600 times more powerful than the actual signal. Your ear can't even begin to pick out a tone until the signal is way, way stronger than that. So this isn't a whisper in a quiet room, this is truly a whisper in a hurricane.
So, how do you prep a message for a journey that's almost guaranteed to tear it apart? Well, you can't just send it out and hope for the best. Instead, WSPR acts like a master map maker. Before the message is even transmitted, it gets encoded with this special kind of map that's going to guide the receiver right through the noise to find the original data.
This whole map-making thing happens in 3 key stages. First, you pack the essential data in as tight as possible. Second, you apply a super powerful error correction code. And finally, you shuffle the bits all around. That's called interleaving. You do that so if a big burst of static comes and wipes out a chunk of the signal, the damage gets spread out across the whole message instead of wiping out one critical part. It makes it way easier to fix later. Let's break these down.
Okay, so WSPR messages are super simple, just a call sign, a location, and a power level. With some pretty slick math, all of that info gets squeezed down into an incredibly small package, just 50 bits. That's it. That's the precious cargo we need to protect.
Now here comes the magic. It's called Forward Error Correction, or FEC. The idea behind it is just brilliant. It's like, hey, we know this message is going to get beat up by noise, right? So let's send along a bunch of extra redundant information in a really specific, structured way. This extra data is like a blueprint that lets the receiver not only see where the errors are, but actually rebuild the original message all by itself. No need to ask for a do-over.
And WSPR goes all in on this. It takes our original 50 bits of data and, using something called convolutional coding, it blows them up into a 162-bit package. Now think about that. We've more than tripled the size of the message. But all that extra data, that's the super detailed map the decoder is going to need to find its way through the noise later. And this isn't just random stuffing. This redundant data is created by a very precise mathematical recipe. At the heart of that recipe are these two 32-bit numbers. They're called the Leyland-Lushbao polynomials. Just think of them as the secret keys to the code. They tell the transmitter exactly how to build that redundant map, and crucially, they give the receiver the exact same recipe so it can check the work later.
All right, so let's jump over to the receiver side. Our message, now packed with its special map, has arrived, but it's buried in noise. To find it, the receiver uses this incredibly smart process called the phono algorithm. Honestly, the best way to picture this is to imagine our decoder is a traveler and the noisy, messed up signal is a huge, confusing maze. This just nails it. Somewhere inside this absolute chaos of static is one single correct path that leads back to our original 50-bit message. The job of the phono algorithm is to be our traveler and to methodically find that one true path while ignoring all the dead ends and wrong turns created by the noise.
So how does our traveler navigate? It's got a kind of statistical compass. For every single bit it looks at in this maze, it can't be 100% sure if it was a 0 or a 1. But using that FEC map we sent, it can calculate the probability. So it might look at a fork in the road and say, okay, there's a 70% chance the right path is a 1 here and a 30% chance it's a 0. And that's its guide.
The search strategy is actually pretty simple. First, the traveler always moves forward down the path that looks most likely. At every step, it checks how well its current path lines up with the map, comparing it against a minimum standard or a threshold. If the path suddenly starts looking bad, the traveler just stops, backtracks to the last good intersection, and tries the next most likely turn.
But here's where it gets really, really smart. The algorithm adapts. As long as our traveler is on a path that seems right and matches the map really well, it actually raises its own standards. It tightens that quality threshold, getting pickier and demanding an even better match to keep going. This is a clever way to keep it from getting tricked and following a long, false path that just happens to look good for a while.
But what if the noise is just too much? The traveler can't just search forever. The algorithm has a limit. If it's forced to backtrack and explore dead ends too many times, it eventually just gives up. It concludes the maze as unsolvable, it times out, and you get a no decode. The whisper was just lost for good.
Now, for any of this to work, for the traveler to even find the entrance to the maze, there are some super strict, non-negotiable rules that every WSPR station on the planet has to follow. And the most important rule of all is timing. Everything runs on a precise 2-minute cycle, perfectly synchronized across the globe. Transmissions don't just start whenever someone feels like it. Nope. They start exactly 2 seconds past the beginning of every even minute. So at 2 minutes past the hour, 4 past, 6 past, and so on. The signal lasts for about 1 minute and 50 seconds, and then everyone listens. This coordination is everything.
And when I say synchronized, I mean synchronized. The clock on every single WSPR computer has to be accurate to within 1 second of Coordinated Universal Time, UTC. Why so strict? Well, the receiver has to know the exact millisecond to start listening for that signal. Without that perfect timing, it's like trying to find the maze entrance blindfolded. You've got no chance.
Okay, so let's pull all these pieces together and see how this amazing process takes what looks like a solid wall of static and turns it into a perfectly clear, readable message. What's really cool about WSPR is that you don't need a giant, expensive lab to get in on the action. The hardware you need is actually pretty basic. All you really need is a stable radio receiver, a regular computer with a sound card to do the math, and of course, that super important, perfectly synchronized clock. And this is what it looks like. This is the payoff. In the WSPR software, you can just barely see these faint signals as these thin little lines on what's called a waterfall display. I mean, they're just smudges, really. But behind the scenes, the Fano algorithm is racing through that maze, and when it finds the one true path, boom, it instantly turns that faint little trace into a perfect decoded message right there on the side.
So, at the end of the day, WSPR pulls off this impossible trick with a combination of 3 brilliant ideas. You've got a clever map, created by forward error correction, that prepares the message for its brutal journey. You've got an intelligent traveler, the Fano algorithm, that can navigate the maze of noise. And the whole thing only works because everyone plays by the strict rules of synchronized UTC timing.
It really makes you wonder, doesn't it? These techniques, they're not just for hobbyists. They're used in things like deep space probes. So if we've built the tools to reliably pull a message from a signal that's hundreds of times weaker than the noise around it, what else is hiding out there in the static, just waiting for the right traveler to come along and find it?